Alright guys, so this is going to be our web lesson for the day, our video lesson for the day. Got a quick couple things to cover first, and then we'll go into some mathematics. First things first, please check out the calendar today. It has changed a tiny little bit since you saw it last. I added one problem to the homework that I think is important, but I'm going over how to do it today, so it's nothing too crazy. I think we've got a birthday today. I think we have 2 birthdays tomorrow, so an exciting couple days. Yeah, sorry that I'm not here today, but I am looking forward to coming back tomorrow. One thing I'd like you guys to do is you did get an email, hopefully, from Mr. Backrote. Mr. Backrote will have sent you the login information and like network key or whatever license key that you need to get Mathematica working at home. If you didn't receive anything from him, please let me know. Also check out your spam filter. I don't know. I don't think it would have gotten filtered though, since it is a 211 email address. If you need the Macintosh version, also let me know. Okay, anyway, so keep me posted on that. Hopefully you guys will be up and running soon for vector calculus at home. Also, if you can open up your vector calculus folder when you get a chance, I'm going to show you where the materials we're going to be working on for the next 5 days are going to be. In the vector calculus folder, if you double click that and you go into lessons, actually the first lesson we're going to be doing is in VC00. It's a reference lesson. It's parametric plotting. We're going to talk about and we're going to review plotting things parametrically, then we'll go on to the multivariable calculus stuff. So take a look in here. Basics and tutorials. It's up to you to read those on your own, guys. That's the textbook. You are going to be spending time doing some reading in class. And then give it a try and literacy. These are the 2 things that are due on Friday. Now give it a try. The problems that are assigned are on my calendar on the web. I believe it's problem number 1. Problem number 2, problem number 4, problem number 5, but you can double check that and make sure. Literacy, that will be handed out to you, and that's something that you do by hand. So you saw that in the, the introduction chapter that I made. Anyway, so if you have any questions about any of that, please let me know when I come back on Tuesday, and why don't we run through our quick lesson right now. We are talking about graphing circles and ellipses parametrically. And this is pretty straightforward, but what I'm going to do is I'm going to kind of build this up from scratch. And so first, why don't we talk about the traditional equation for the unit circle. The traditional equation for the unit circle in rectangular coordinates, it's x squared plus y squared is equal to 1, centered at the origin, radius of 1. Parametrically, you guys actually know this equation for the unit circle like the back of your hand, because you have studied it extensively. It's the x-coordinate is cosine, the y-coordinate is sine. It's that exact same unit circle that you guys studied when you were in Trig Calc A and that you used extensively last year. One thing that you're going to be able to tell, which is kind of neat, is you can kind of prove to yourself that these 2 equations are synonymous, that these 2 equations describe the same mathematical phenomenon. If you take this x of t and this y of t and you substitute them into the traditional formula here, you can see that one equation satisfies the other. So x squared plus y squared is equal to 1. Replace x with the cosine of t, replace y with the sine of t. Well, that's our traditional Pythagorean identity, right? That's the Pythagorean identity. We know that sine squared plus cosine squared is equal to 1. So check, we just proved it. These 2 equations are synonymous. They're just written in a different way. We say that the equation over on the right is a parameterization of this traditional formula, x squared plus y squared is equal to 1. Now lots of different kinds of curves in space can be parameterized. Not every curve in 2-dimensional space can be parameterized, so this is not a technique that we can use every single time, but for our purposes this year, the vast majority of the time, we are going to describe our equations parametrically, and we are going to see less and less of this traditional form. There are many good reasons for that, but for the most part, the reason is the parametric equations are going to be a lot easier to work with. You're actually going to see that happen during this lesson today, that parametrically a lot of these equations are going to be a lot nicer to describe. Now one thing that I could say is another way to write this parametric equation is c of t. I picked c for circle. Circle as a function of t is equal to the cosine of t comma sine of t. It's a set of ordered pairs that as you change your t, you get different ordered pairs, and from time equals 0 to time equals 2 pi, you get an entire circle graphed out. Now let's say that that I, instead of wanting to do a unit circle with a radius of 1, I instead want to expand my circle out to have a radius of r. I know that doesn't look like a circle, but if I want to expand out to a radius of r, for the traditional rectangular form, it's x squared plus y squared is equal to r squared. Parametrically, you would say, instead of cosine comma sine, you say r cosine r sine. What you're doing is you're taking the x coordinate and the y coordinate and you are expanding them out both by a factor of r. And in fact, you could also write this as c of t is equal to r times cosine comma sine. You're taking this unit circle, this cosine comma sine, and you are expanding it by a factor of r. You're basically dilating the unit circle by a factor of r. Now I'm going to erase all of this junk here so I have a nicer picture. So think of this as dilating the unit circle by a factor of r. Here's our unit circle. If we multiply the x and y coordinates all by r, there it is. We're expanding out, in this case, by a factor of 4. But, more generally speaking, it's a factor of r. Now let's say instead of leaving our circle centered at the origin, instead of leaving a unit circle centered at the origin, let's say that we want to move things around in the xy plane. The traditional way of writing this is x minus h quantity squared plus y minus k quantity squared is equal to r squared. Parametrically, this is x of t is equal to r cosine of t plus h, and y of t, the y coordinate, is r sine of t plus k. So what we're doing is we're still dilating by a factor of r, whatever we want our radius to be, just multiply by that, and then this h and this k, it's a translation. Now here's a nicer way to describe this. Here's our original unit circle, cosine comma sine. We're dilating by a factor of r, and then what we're doing is we're taking the center and we're moving it by h comma k. We're translating in the xy plane by h comma k, by an ordered pair, a point in space. I could show you that. So think of this as dilating the unit circle by a factor of r and translating by the point h comma k. By the way, I should remind you guys, this is a video. I mean, you know that, but this is a video, so videos can be paused, they can be rewinded. So if I am going too quickly, or if you miss something that I say, or if I don't give you enough time to take some notes, just let your substitute teacher know, and he or she will be happy to click pause or rewind so you can get the notes that you need. But in any case, so let's take this c of t. Let me show you what I mean by this. So here's our unit circle plotted onto the xy plane, and here's a circle that has been translated. Its center has been translated to the point 1, 1, and it's been dilated. It's been expanded out. Its radius is now, it looks like a radius of 3. So I guess if you wanted to write this, it would be radius of 3, so 3 times the cosine of t, comma sine of t, and then looks like the center has been moved by 1 in the x direction, 1 in the y direction, so plus 1, comma 1. That's one way of writing the equation. You can also write it as a single ordered pair rather than like two ordered pairs added together. You'd say 3 cosine t plus 1, comma 3 sine of t plus 1. And that would be another way that you can write that equation. So, I don't know, kind of a neat way to describe circles parametrically. Now, we're not actually limited by circles. We can also do ellipses, and that's kind of the cool thing about this parametric way of describing the unit circle, because we can take this base unit circle and stretch it in the x direction, stretch it in the y direction, move its center around, and we could describe any ellipse or circle in the plane just with that small change. So the traditional form, if you want to write it down, but you're not going to need it too often, is x minus h all over a quantity squared plus y minus k all over b quantity squared is equal to 1. This is a traditional formula that you would have to memorize, but parametrically, really all you need to do is instead of this like over a and over b for your stretching of your ellipse with the traditional formula, we're still dilating our unit circle, but we're stretching a different amount in the x direction and a different amount in the y direction. And then we still have our translation by h and k at the end. Now you can also write that as a cosine comma b sine plus the point, our translation of h comma k. So think of this as dilating the unit circle by a factor of a in the x direction, a factor of b in the y direction, and then translated by the point h comma k. So you're starting with this base unit circle, you're stretching in whatever direction you need to stretch, you're moving the center in wherever you need to move it, and there, I've got this little orange ellipse right here, and actually our next example will be to find an equation for this guy right here. What's our equation? And we're going to do a little bit of work with it. I'll show you that we can actually do calculus with these sorts of equations. It's very doable. And it's a good thing we can do calculus with these sorts of parametric equations, because this is what we're going to be doing pretty much all year. All of this kind of traditional XY way of describing equations, very rarely are we going to do too much with that. It's typically going to be parameterizing things. Okay, so find the traditional and parametric equation for the orange ellipse. And so here's the basic equations that we had from the previous slide. And here's our unit circle. And there's our orange ellipse. So I guess what we should do here is look and see where our center is. Looks to me like we're centered at the point 1, 3. And then we can look at our major and minor axes. It looks like our major axis is 2 in, our semi-major axis, right? Because that's half of the major axis right here. Half of the major axis is a length of 2 in the x direction. Our semi-minor axis, half of our minor axis in the y direction is 1. And so here and there. X minus 1 over 2 all squared plus y minus 3 all over 1 quantity squared equal to 1. All right, parametrically, this is a lot easier to do because you don't really have to memorize quite as much. You just remember where you're stretching things. You're just working with that unit circle. So we're stretching in the x direction by a factor of 2, so that a is going to be 2. B, we're not stretching at all in the y direction, so leave that b as a 1. And then h comma k, we are moving the center of our ellipse. We're translating by 1 to the right and 3 in the vertical direction, 3 up, so the point 1, 3. There it is. C of t is equal to 2 cosine t comma sine of t plus the point 1, 3. Now you can write this all together if you really like to. 2 cosine of t plus 1 comma sine of t plus 3. So that's another way of doing it. You could separate it. You can write this as, two separate components, x of t and y of t, which just really depends on your preference. All three of these, 1, 2, and 3, all three ways of writing this parametrically are mathematically correct. So, okay, and then I've got a quick little example we're going to work through here. Find the rightmost and bottommost points on the orange ellipse. Now I know we don't need calculus for this, but we're going to use calculus for it. And find the equation of the tangent shown at, it says x equals 3. It's supposed to be x equals 2. So just tweak that in your notes for me. Okay, so to find the rightmost and bottommost points on the orange ellipse, if you think about the rightmost point, you can think of that as maximizing the x-coordinate, right? So we already know the answer right here. We know that the rightmost point is 3, 3, but what we're doing is we're going to maximize. Oh, that's really messy. We are going to maximize the x-coordinate, so we're going to maximize x of t for the rightmost point. Likewise, if we're trying to find, I guess in this case, the bottommost point, we're going to be minimizing the y-coordinate. So we're going to minimize the function y of t. Okay, so here's the equation that we got on the previous page. X of t is 2 cosine t plus 1. Y of t is sine of t plus 3. So to find the rightmost point on this orange ellipse, if we maximize x of t, we're in good shape. To find the bottommost point on the orange ellipse, if we minimize y of t, that's going to give us our bottom point on the ellipse. Okay, so I guess if we're minimizing and maximizing, we should take the derivative and set it equal to 0. So here they are. X prime of t is negative 2 sine of t. Y prime of t is the cosine of t. Okay, so in this case, if x prime of t is negative 2 sine of t, set that equal to 0 and solve. That gives us two possible points. It's t equals 0 and t equals pi. Those are the two times at which our derivative is equal to 0. What we could do is we could test both of them. Take x of 0 and y of 0. Take x of pi and y of pi. Those are the 2 points on our ellipse that I guess these are like our critical values here, our critical points. At 3, 3 and at negative 1, 3 we have our leftmost point and our rightmost point. Now we were asked for the rightmost point, so once we've tested our critical values in the original function, we see that the rightmost point is right here, 3, 3, and negative 1, 3 is not the rightmost point. In a similar vein, to get the bottommost point, all we really need to do is we are minimizing y of t. That involves taking y prime of t, which turns out to just be the cosine of t. We're setting it equal to 0. And we get two times at which this happens, at pi over 2 and 3 pi over 2. Now, you can kind of see that, 90 degrees up from the center, 90 degrees down from the center. Those are the two candidates. Now we could find the coordinates of those two purple points, this bottom point and this top point, just by plugging back into the original function, x of pi over 2, y of pi over 2. That's the point 1, 4. You get that just by plugging back in to these guys. You plug t equals pi over 2 back into those original parametric equations. Now you could do the same exact thing with 3 pi over 2. So x of 3 pi over 2 and y of 3 pi over 2, that gives us the point 1, 2. Looks like that's our bottommost point right there. 1, 2. And 1, 4, we're going to throw that out because it doesn't really give us the bottommost point. That's another extreme value, but that's the topmost point that we're not looking for. Okay, in any case, I know this is mostly review here and that you've seen a lot of this stuff last year, but at least you've seen parametric equations. But this way of graphing circles and ellipses parametrically in a really general form, that I think is kind of new. So I wanted to make sure you guys could see that we can really do calculus on these sorts of equations. And it's pretty simple calculus too. If you look, this did not take a lot of work to get these extreme values. Now for ellipses, I realize it's kind of useless using calculus to get these extreme values. But imagine if you had a much more complicated parametric equation, then the tools of calculus would be very, very useful. I just wanted to start simple and then we'll build up to harder stuff as the year goes on. Now I did have one more part of this question that I was supposed to answer. They ask for the equation of the tangent at x equals 2. So this little tangent line right here in green, we're going to find the equation of that tangent line. Yeah, it's just kind of a cool problem to try to do, so let's give it a try. I'll clear out all the stuff we had, And remember, parametrically, we have our orange ellipse. I just put it up on the screen right here. And we had our derivative, the derivatives x prime of t and y prime of t that we just found on the previous slide as well. And you might not remember this from last year, but if you're trying to find dy dx, the change in y with respect to x, really all you need is x prime of t divided by, y prime of t divided by x prime of t. One way to understand that is dy dx is really the same thing as dy dt times dt dx, right? You can think of those dt's canceling. Well, that's the same thing as doing y prime of t divided by x prime of t. So that's where that formula comes from. But in any case, make sure you have that in your notes. dy dx is the same thing as y prime of t over x prime of t. Now you'll see that in the textbook as well, but we're going to use that because that means that our dy dx, our slope at this point x equals 2, is going to be described by, in this case, cosine of t divided by negative 2 sine of t. If you want to use some, whatever, some trig identities, very simple trig identities on here. Remember that cosine divided by sine is cotangent. So we could think of this, this slope at any point on this ellipse being described by the function negative 1/2 cotangent of t. So now all we need is the time at which, so whatever this angle is, the time at which we're at this particular point on our ellipse. The point at which x equals 2 on our ellipse. So I have x of t, remember, is 2 cosine of t plus 1. That was given to us. Or not given to us, we found that on the previous slide, so it was given to us for this part. And we're trying to find when x of t is equal to 2, so plug it in. 2 equals 2 cosine of t plus 1. So 1 is equal to 2 cosine of t. You're just subtracting 1 from both sides. That means we're looking for when the cosine of t is equal to 1/2. Now, if we're looking for when the cosine of t is equal to 1/2, you guys have all memorized your unit circle very, very well. Hint, hint. And if you don't remember it, you've got that calculus review sheet to study. But in any case, the particular angle that we're looking for, I know that I missed one here. There's another one that we could have had as a candidate. We're looking for pi over 3. We know graphically that pi over 3 is that angle we're looking for, or in this case we can think of it as a time, since parametrically we kind of work with time. Okay, if we take these two pieces of information and we put those two pieces of information together, this negative 1/2 cotangent of t, and we're looking for the slope at the particular time, pi over 3, just plug one into the other. Dy dx evaluated at t equals pi over 3 gives us negative root 3 over 6. Now that's once again involves a little bit of unit circle knowledge, but it's not actually that bad since cotangent of t, remember, was just cosine over sine. You know what the cosine of pi over 3 is. You know what the sine of pi over 3 is. So if you just put it all together in a clever way, you get that negative root 3 over 6. That is the slope of this green line right here. Now you can kind of verify to yourself if this makes sense, because this has a negative slope, and this is a negative slope that we just found, so it seems like it makes sense. Of course, that's not the equation of the tangent. That's just the slope of the green line. So to get the equation of the tangent, we need the x-coordinates, or an x-coordinate of a point on the graph. We need a y-coordinate of a point on the graph, and we need the slope. We'll put that all together on this final slide of this presentation. So here's the final slide. And so at the time pi over 3, right here, we have an x-coordinate of 2. You could check it and see if it makes sense. Looks like it makes sense. And then we have a y-coordinate of 3 plus root 3 over 2. Seems about right. If you take a look right here, this point, it's a little bit above 3. So 3 plus a little bit more. Seems like it makes sense. And finally, we already found the slope of the green line on the previous slide, negative root 3 over 6. So here it is all put together. I did this in point slope form. I know it's not a beautiful way of writing this, but the nice thing about point slope form is it's quick and easy, and we're done with the problem really fast. So I just put the y coordinate in, the x coordinate in, that slope in. I put all these three pieces of information in together, and we've got our answer. Now, if you have a strong need to put this into slope-intercept form, you can go ahead and do so. Personally, I wouldn't spend my time on that if I were you guys, and here's the reason for it. This is an xy equation for a line. Within a couple of days, we're not going to be using xy equations for lines very much anymore, and we're really going to be using parametric equations for these lines. Parametrically, this line's pretty easy to describe as well, but you don't need it for this first homework assignment, and so therefore we're not going to worry about it today. We might start talking about it later in the week. So for now, xy equation in point slope form, and we're all good. I really wish that I could ask if there were any questions, and I wish I could answer some of those questions, but unfortunately it will have to wait for tomorrow. So good luck. Go ahead and open up that vector calculus folder for me and start reading through the basics in the tutorial. Check the calendar, start that give it a try stuff, and I'm looking forward to seeing you guys tomorrow. Have a good one.